So I want to start by saying that HDLs are slightly different than our other lipoproteins we've been discussing. The principal function of HDLs, or high-density lipoproteins, is to transport excess cholesterol obtained from peripheral tissues back to the liver. These particles can be generated by several mechanisms. However, they're primarily secreted from the liver and the intestine. And they remain relatively small molecules whose shell, like that of other lipoproteins, contains some phospholipids, free cholesterols, and a variety of apoproteins. However, there's very low contents of triacylglycerols or cholesterol ester initially found in the hollow core of these early nascent HDLs. So HDLs are highly characteristic of ApoA, and as we've seen previously, they also carry ApoC2 and E, which they donate to both VLDLs and chylomicrons. So before we talk about reverse cholesterol transport using HDLs, I want to first discuss several key enzymes we'll need to know. So the enzymes we need to discuss before talking specifically about HDLs are listed here. And that's ACAT, LCAT, and our family of ABC transporters. Before we discuss the specific enzymes, let's first talk about the pool of cholesterol within the cell. So cholesterol will be found in two major forms: unesterified cholesterol, which is primarily found in cell membranes, and esterified cholesterol, which functions as a storage form. The esterification of cholesterol makes it more hydrophobic, and therefore it will be more readily stored as lipid droplets. So to flux between these two pools, we have the enzyme ACAT, which is acyl-CoA acyltransferase. And this enzyme will esterify unesterified cholesterol into our storage form. We can free our storage form through a cholesterol ester hydrolase. Now, the unesterified cholesterol pool is highly regulated, and HDL, we'll see, is responsible for the efflux of cholesterol from the cells to the liver. So to move cholesterol from the cell to the HDL, we must first de-esterify the cholesterol, and then it's moved through a family of transporters. The family of ABC transporters is involved in active transport that requires ATP. There's two illustrated here, ABCA1 and ABCG1, and these are distinct based on the preference of lipid in which they transport. Cholesterol is primarily transported through our ABCG1. So once we've transported cholesterol and phospholipid across the cell to store it and trap it in an HDL, we need to re-esterify the cholesterol. And the enzyme responsible for that is LCAT, or lecithin cholesterol acyltransferase. So this will esterify the cholesterol such that it's trapped within the HDL core. So the other thing to note about the structure of HDL here is it's characteristic again of ApoA. So the other interaction to be aware of that HDL has with VLDL is through the enzyme CETP, or cholesterol ester transfer protein. And this enzyme transfers cholesterol ester from HDL in exchange for triacylglycerols from VLDL. This exchange allows for the redistributions of lipids between the two particles during circulation. In the process of maturation of our nascent discoidal HDL, the particle in circulation will accumulate cholesterol, cholesterol esters, and phospholipids from our peripheral tissues. And that's in a transport mechanism using our ABC transporters, as we discussed previously. And as the HDL becomes loaded with these lipids, it starts to take on a more spherical shape. So the major benefit of HDL particles derives from their ability to remove cholesterol from these cholesterol-laden cells and transport the cholesterol back to the liver. The primary means of clearance of HDL from the blood is through the uptake by the scavenger receptor, SRB1. And when the HDL particle is bound to the receptor, the cholesterol, cholesterol esters, and phospholipids are transferred into the hepatocytes. And when the HDL is depleted of these lipids, the particle can dissociate from the receptor and re-enter circulation. So I'm going to take this opportunity to use this slide as an overview of what we've discussed this week so far. It gives you an idea of the interactions of chylomicrons, VLDLs, and HDLs before we add on cholesterol synthesis and LDL uptake. So if we start again with our diet, remember dietary lipids, cholesterol esters, cholesterol, as well as triacylglycerides are transported by chylomicrons. Chylomicrons require an interaction with HDL to receive ApoE and ApoC2, and they mature through an interaction with lipoprotein lipase, which is mediated by ApoC2. Our remaining chylomicron remnant will be taken up by the liver. Next, we have our VLDLs, and remember these are carrying triacylglycerols, cholesterol, and cholesterol esters that are synthesized in the liver. VLDLs have several key interactions with HDL, the first of which being the acquisition, again, of ApoE and ApoC2. And this new interaction we just discussed using the enzyme cholesterol esterase transfer protein, where VLDLs and HDLs can exchange triacylglycerols for cholesterol esters in circulation. VLDLs mature through an interaction again with lipoprotein lipase, and the VLDL remnant, IDL, can be taken up by the liver or continue to mature to an LDL particle, which primarily carries cholesterol and cholesterol ester. We'll look specifically at the uptake of LDL in the next session. Finally, we have our HDL particle, which is in circulation associated with ApoA, our enzyme CETP, as well as LCAT. HDL's primary role is reverse cholesterol transport, so moving cholesterol from peripheral tissues back to the liver. And we'll see that this is very important, as the only means of disposing of cholesterol from the body is through bile acid synthesis. So you'll notice that all of our particles, chylomicrons, VLDLs, and HDLs, can contribute to our unesterified cholesterol pool. In our next discussion, we'll see how the levels of this pool of cholesterol influences the synthesis of cholesterol itself. All right, I think that's all for now, so we'll finish with this summary and move on to next week.